The word transformer is so ordinary you probably stopped hearing it years ago. It appears on utility poles, on appliance labels, in the footnotes of engineering textbooks. You use it as a description of something modern and inevitable. It is not. It is the surviving vocabulary of a copper coil system that powered entire cities for 12 consecutive years before it was methodically removed from service, from institutional memory, and from the official record of electrical history. Not because it failed, not because something demonstrably better replaced it. I found this while tracing the origins of electrical terminology. The more I followed it back, the less the disappearance made sense. In 1883, in a machine room on the Vieux-Pont in Turin, a French engineer named Lucien Gaulard and his English business partner, John Dixon Gibbs, demonstrated something that should have permanently attached their names to the centre of modern electrical infrastructure. Their device was a coil of copper wire wound around an iron core. Not a power source, not a generator, not a battery, a transformer. It took electrical current at one voltage and delivered it at another, stepping power up for efficient long-distance transmission and stepping it back down at the point of use, where it became safe enough to enter a building. Every engineer who examined it understood immediately that this was the solution to the central unsolved problem in electrical distribution: how to move power across a city without losing most of it to resistance in the wire. The mechanics were elegant in their simplicity. Gaulard wound two separate copper coils around the same iron core, one for incoming current, one for outgoing. An alternating current in the first coil induced a corresponding current in the second through mutual induction, a principle that James Clerk Maxwell had described theoretically, and that no one before Gaulard had made commercially functional at scale. The ratio of wire turns in each coil determined the transformation. 10 times more turns on the output side delivered 10 times the voltage. The physical object itself was roughly the size of a large hat box, a cylinder of laminated iron wrapped in copper wire, modest in appearance, extraordinary in function. It required no fuel. It consumed no material as it worked. It did not wear out in the way that moving parts wear out. Turin became the first test at scale. In 1884, the city installed a Gaulard-Gibbs distribution network running from a steam generating station at Lanzo, 40 kilometers distant, along transmission lines strung between wooden poles to substations at the city's edge. The secondary generators stepped the voltage down for use in electric lighting. The system powered over 300 arc lamps across the city centre. The Electrical Review described the Turin installation as the most complete practical demonstration of long-distance electrical power transmission yet achieved. The Italian government awarded Gaulard and Gibbs a silver medal at the Turin Electrical Exhibition. Engineering journals in France, Germany, and the United States reprinted the specifications. They were invited to London. The system ran. It ran continuously. I found the operational records of this period while searching for something else entirely, trying to trace why the word primary, as used in electrical engineering, appears in documents predating every device it is now used to describe. When I followed the citation chain back far enough, I arrived at Gaulard's original design notes, where the incoming coil was labelled the primary circuit and the outgoing coil the secondary. Those terms are still in use today, in every electrical engineering curriculum in the world, in the same meaning, describing the same relationship between wound copper coils. The vocabulary survived intact. The name attached to it did not. During the 12 years between the first Turin installation and the effective end of Gaulard's involvement in the technology, secondary generator networks were installed or proposed in London, Budapest, and several smaller Italian and French cities. The electrical engineer reported in 1886 that the Gaulard-Gibbs patent represented the foundational claim in alternating current distribution, without which no commercially viable long-distance power network could be constructed. That assessment was technically correct. It was also, as it turned out, commercially inconvenient for a number of entities who had come to understand the same thing. In 1885, a young engineer named William Stanley travelled to Pittsburgh and examined a secondary generator purchased from Gaulard and Gibbs by the Westinghouse Electric Company. George Westinghouse had paid $2,000 for the device and its associated patent rights, recorded in the company ledger as a routine equipment acquisition. Not landmark purchase, not a strategic investment. Routine. Stanley's assignment was to understand how it worked and, if possible, improve it. He succeeded. Within a year, he had redesigned the coil connections from series to parallel, stabilized the voltage output, and filed a new patent under the Westinghouse name. The patent application did not cite Gaulard. The press release accompanying the Westinghouse system's public debut in Great Barrington, Massachusetts, in March 1886 described the technology as an American invention. Gaulard was in Paris by then, contesting patent challenges in French civil courts. He was losing. He would be committed to a psychiatric facility the following year. No surviving commercial patent bore his name. I keep returning to the $2,000. The entire foundational claim in alternating current distribution, the patent that the electrical engineer had called indispensable, changed hands for $2,000. And the system that would eventually replace the secondary generator network was, at its core, the secondary generator network with better engineering around it. Not a new invention, not a superior principle, not a different physical logic. The same wound copper coils, the same iron core, the same mutual induction, the new order purchased with the currency of the old. The Great Barrington demonstration ran successfully. Within 2 years, alternating current distribution was expanding across American cities at a pace that older direct current networks could not match. The War of Currents, as popular histories would later name it, is usually told as a contest between two visions of how electricity should move through cities. That framing is accurate as far as it goes. What it omits is that the technology at the centre of the winning argument had been purchased from a French engineer for $2,000 and patented under a different name. I want to be careful here. The Westinghouse engineers made genuine contributions, not minor ones. William Stanley's parallel connection was not a trivial modification. It solved the voltage stability problem that had constrained the Gaulard-Gibbs system to smaller and more controlled installations. Nikola Tesla's polyphase motor, which Westinghouse acquired in 1888, extended the technology into industrial applications that Gaulard had never attempted. The system that emerged from Pittsburgh was more capable than the one demonstrated in Turin. The refinements were real. The improvements mattered. I am not suggesting otherwise. What I am noting is what the improvements required. Every engineer who worked on the alternating current transformer in 1886, 1887, and 1888 had studied the Gaulard-Gibbs patents. The patents were public documents. The operating principle, mutual induction between wound copper coils sharing an iron core, was identical in the original and in every successive design. You could not improve the transformer without first understanding the secondary generator. The new device was the old device with better engineering around it. The new financial order was purchased with the currency of the old. I keep returning to that detail because it suggests something about the relationship between these systems that the official history tends to obscure. A man named Charles Zipanowski makes this transition uncomfortably visible. A Hungarian engineer working for Ganz & Company in Budapest, Zipanowski had installed one of the largest Gaulard-Gibbs secondary generator networks in Europe, a system supplying the Budapest National Exhibition of 1885, feeding over 1,000 incandescent lamps across the exhibition grounds from a central generating station. The Electrician Journal documented the installation in detail. Then, in 1885, Zipanowski filed his own transformer patent with two colleagues, Otto Blathy and Mixer Dairy. The patent cited mutual induction. It did not cite Gaulard. In 1889, Zipanowski published a technical retrospective on the development of the transformer. He described the Gaulard-Gibbs secondary generator as a preliminary experiment. Gaulard was by then in the Sainte-Anne Asylum in Paris. He died there in 1888. He was 36 years old. No obituary ran in the Electrical Review. The formal phase-out of the secondary generator's name from the technical record did not arrive through a single decision. It accumulated through patent language, through journal attribution, through the gradual substitution of one set of citations for another. By 1890, the standard engineering reference for the transformer was the Westinghouse patent. By 1895, Gaulard appeared in technical histories only in footnotes. The device he had demonstrated in Turin in 1884, the one praised in 3 countries, awarded a silver medal, installed across multiple European cities, had been reclassified, not superseded, reclassified. The cities it had powered became test sites. The 12 years of operational infrastructure became a period of experimentation. The language of historical revision is always bureaucratic, the implications are not. The Turin secondary generator network was formally decommissioned in the autumn of 1896. The decision was made by the Società Promotrice dell'Industria Elettrica, the municipal utility body that had assumed operational control of the city's electrical infrastructure. The director, an engineer named Emilio Ferrero, recorded his rationale in a document preserved in the Utilities Administrative Archive. His description of the existing network, functionally superseded by modern transformer installations. 6 words. No ceremony, no archive deposit, no acknowledgement that the network being decommissioned had operated continuously for 12 years and provided the foundational operational proof for the technology that was replacing it. 2 technicians were assigned the physical work, not supervisors, not engineers, technicians. A Piedmontese wireman named Battista Cane and his assistant Renato Fossati began with the substation on the Via Nizza, working through October 1896 with insulated handled cutters and ceramic standoff insulators stacked in crates for eventual reuse. The coil housings themselves, the hatbox-sized cylinders of wound copper and laminated iron that had transformed voltage across Turin's streets for more than a decade, were lifted from their mounting frames and stacked in a maintenance yard behind the central station on the Corso Vittorio Emanuele II. No inventory was filed, no engineering drawings were retained. The coils sat in the yard through the winter, oxidizing at the edges where the weather reached the copper windings, rusting at the iron cores, waiting for a decision that no one was in any hurry to make. In the spring of 1897, Battista Cane reported to his supervisor that the coil housings in the maintenance yard had begun to corrode visibly. The copper windings were oxidizing where the weather had reached the outer layers. The iron cores were rusting at the edges. A decision was required. The utilities records show that the question was referred upward twice before reaching Emilio Ferrero, who responded in a single sentence: sell the copper for scrap and dispose of the iron. No provision was made for preservation. No specimen was retained for the utility's own technical archive. No communication was sent to the Polytechnic Institute of Turin, which was at that moment actively teaching courses in electrical distribution, using principles the coils in that yard had demonstrated for 12 years. Cane and Fossati broke the housings apart over 3 days in April 1897. The copper was weighed, bundled and sold to a metals dealer on the Via Arsenale for 43 lire. The iron was carted to a foundry on the Strada di Settimo. By the end of the month, the physical record of Turin's secondary generator network had been reduced to 2 entries in a scrap ledger. Ferrero was asked about the decommissioning decision some years later in a 1903 interview with the journal L'Elettricità. His response was recorded verbatim. Those devices belong to a transitional period. One does not preserve the scaffolding after the building is complete. Within 8 years of the Turin decommissioning, the working knowledge of how to operate a Gollard-Gibbs secondary generator network had effectively vanished from the engineering profession. Not because the underlying principle was forgotten. Mutual induction remained the foundation of every transformer built after 1886. But because the specific operational knowledge of that particular system, its calibration tolerances, its failure modes, its maintenance procedures, was embodied in the engineers and technicians who had run it. Those men had moved on to newer systems. The journals that had documented Turin and Budapest had moved to covering Westinghouse and Tesla. By 1905, an electrical engineer encountering a surviving Gollard-Gibbs coil housing would have recognized the operating principle, but not the operational history. By 1910, the device would have required archival research to identify it all. 726 years for tally sticks to be forgotten after burning, 13 years for this. The vocabulary, however, survived completely intact. The word transformer, the term that displaced secondary generator in common use by the early 1890s, carries inside it the logic of the original device, a thing that transforms electrical potential from one level to another through mutual induction between wound copper coils. The words primary and secondary, as applied to transformer windings, are direct translations of Garland's original design language. Every electrical engineering student who learns those terms today is using vocabulary coined to describe a device whose inventor died in a psychiatric facility at 36, in the same year that Westinghouse was publicly describing the transformer as an American achievement. The language remembers, the coils are gone, maybe this is simply the history of technology. Systems are superseded. Better engineering replaces adequate engineering. Patent law rewards the improver rather than the originator, and that is not always unjust. Genuine improvements matter. The simplest explanation is that Gaulard's system was limited. that the engineers who followed him solved problems he could not, and that the reallocation of credit, while harsh, was commercially and legally predictable, negligence rather than design, institutional forgetfulness rather than institutional decision. A clerk sold the copper because no one told him not to, except I keep returning to the 43 lire. The copper sold for 43 lire. The iron went to a foundry. No one wrote to the Polytechnic Institute. No one retained a single specimen. The Gollard-Gibbs patents were public documents, retrievable today in national patent archives in France, Britain and Italy. But the physical objects, the actual wound copper coils that had transformed voltage for 12 years across the streets of Turin, were sold by weight to a metals dealer who presumably melted them within the week. What does it mean that the only surviving record of the secondary generator network's operational life is a scrap ledger entry and 2 lines in a utility archive? What happened to the installation drawings, the maintenance logs, the calibration records that any functioning urban electrical network would have required? What system powered entire cities for 12 years and left behind less documentation than a single municipal budget report? Why did no one at the Polytechnic Institute, at the Royal Society, at any of the engineering societies that had praised the Turin installation, think to request a specimen before the yard was cleared? And why, when you reach for the word that describes the device at the centre of every power grid on Earth, do you find yourself holding a term coined to replace the name of the thing it describes? The word is still there on every utility pole, every appliance label, every electricity bill you have ever received. The transformer. The language remembers what the scrap ledger erased. The coils are gone. The word remains.